You are behind the wheel right now. You have exactly 75 minutes before you pull into your destination, and your entire future is writing on an exam.
Yeah, an exam covering a seriously massive, dense paper. I mean, a comprehensive overview of large language models is not light reading.
No, it is not. And you're stressed. You can't look at a whiteboard. You definitely cannot read complex math equations while you're navigating traffic, so take a deep breath.
Keep your eyes on the road. We've got you.
Exactly. Let's establish the ground rules for the next hour and 15 minutes. We're going to get you through this entire paper, step by step, for this deep dive. And we're using only words, analogies, and real-world mechanics.
Right, no math required on this drive.
None. We'll do periodic milestone recaps so you don't lose the thread. By the time you park your car, you will intimately understand the landscape, the architecture, the training loops, the fine-tuning, and the physical hardware challenges of modern AI.
The mission is so vital right now, and the timing is perfect. I mean, this paper isn't just some textbook. It's basically a treasure map of how the AI industry completely transformed in just, like, a few short years.
Yeah, we're breaking down how we went from simple autocorrect programs to machines that can, write software or analyze legal documents.
Or even plan physical tasks in the real world.
Which is still crazy to me. But before we get into the granular details of how these systems are built, we need the 30,000-foot view. Like, what actually qualifies as a large language model according to this specific paper?
So the authors draw a very strict line in the sand here. An LLM is a model with 10 billion parameters or more.
10 billion.
Right. Anything smaller than that, they classify as a PLM, which is a pre-trained language model.
Got it. And the paper outlines this whole evolutionary timeline, right? Like, first we had traditional natural language processing.
Yeah, models meticulously trained to do just one specific thing, like detecting spam or translating French to English.
Right, and then we moved to those PLMs, which learned a general understanding of language, but they still needed a lot of manual handholding to be useful.
Exactly. And finally, the industry just decided to scale everything up massively.
Which is when we hit that 10 billion parameter threshold. And something totally bizarre happened, right? By getting massively scaled up, these models developed what the paper calls emergent abilities.
Emergent abilities. That is a massive concept for the exam. It represents a profound paradigm shift in computer science.
How so?
Well, traditionally, if you wanted a computer to do something, say, solve a logic puzzle, you had to explicitly write the code for solving logic puzzles.
Right, you write the rules, the computer follows them.
Exactly. But with LLMs, researchers discovered that when you scale the neural network up to massive proportions and just feed it a significant chunk of the internet, it starts doing things it was never programmed to do.
Like what?
It starts reasoning, it begins planning, it translates languages it was never explicitly taught.
Oh, wow, so the logic didn't come from human programming at all.
No, it didn't. The logic emerged organically as a byproduct of sheer scale and data density.
That concept alone is wild to me. It really reminds me of physics, like how water doesn't have the property of wetness when you just look at a single H2O molecule.
Oh, that's a great analogy.
Yeah, but when you put billions of them together, wetness just kind of emerges. So to understand how a machine suddenly starts reasoning like a massive body of water, we have to look at the individual molecules.
We have to start with the foundational building blocks of the neural network. Let's call this the engine room of the AI.
The engine room. I like that. The paper outlines 4 essential components that make up any modern LLM: tokenization, positional encodings, attention mechanisms, and activation functions.
These 4 components are literally the physical gears and pistons of the model. If you understand these, you understand how an AI reads.
Let's start with tokenization, because the intuitive assumption most people make is that an AI just reads words, right? Like we do.
But it doesn't.
Right. You can't just feed the word unbelievable into a math equation. Tokenizers, like byte pair encoding or word piece, they chop the text into usable chunks.
Yeah, exactly.
I always think of it like prepping ingredients for a stew. You don't throw a whole unpeeled onion into a pot and expect it to cook right. You chop it. But how you chop it really matters.
It matters a lot.
It's like the tokenizer might chop unbelievable into unbelieve and able.
Yeah, and the primary reason for chopping the text into subwords, rather than just feeding in whole words or individual letters, is raw efficiency.
Efficiency.
Imagine if the model had to learn every single word in the English language, plus every misspelling, plus every slang term, as a totally unique entity.
The dictionary would be huge.
Infinitely large and computationally impossible to process.
Huh.
But on the other end of the spectrum, if you just fed it single letters A, B, C, The model would have to work incredibly hard just to figure out that CAT means an animal.
So subwords are kind of the Goldilocks zone.
Precisely. By breaking things into subwords, the model relies on a finite set of tokens, usually around 30,000 to 100,000 unique pieces.
Okay, that makes sense.
And the brilliance of this approach is how it handles the unknown. If a user types a completely made-up word, the tokenizer doesn't crash.
Oh, because it just breaks the made-up word down into smaller phonetic chunks.
Exactly. Prefixes and suffixes, it already knows.
Yeah.
It is an elegant mathematical solution to the infinite variability of human language.
Okay, so we have chopped our ingredients. The text is now a sequence of tokens. The engine inside almost all of these models is the transformer architecture, right?
That's the one.
Now, from what I understand, older AI models, like recurrent neural networks, they read text the way humans do, word by word, left to right.
Right, sequential processing.
But the transformer is different. It ingests all the tokens at the exact same time. It processes everything in parallel to save time.
It does.
But wait, if it reads the whole sentence simultaneously, how does it know the difference between the dog bit the man and the man bit the dog? Those are the exact same chopped ingredients in the exact same quantity.
That is the big question. Because the transformer essentially sees a bucket of tokens rather than a sequential line of text, it has a glaring blind spot regarding order.
And that's where the second component comes in.
Exactly. That blind spot is exactly what positional encoding solves. We have to artificially stamp a time code, or like a spatial coordinate, onto the mathematical representation of each token before it enters the network.
It's like sticking a numbered label on every single piece of chopped carrot and onion before throwing them in the pot, so the chef knows exactly what order they were sliced.
I love that, yes. And the paper discusses the evolution of how we apply those labels. Two very specific types of positional encodings dominate modern LLMs, and these are crucial for your exam.
Let's hear them.
ROPE, that's R-O-P-E, rotary positional encoding, and alibi.
Okay, ROPE and alibi.
Earlier models used absolute positional encoding, simply saying, this is word 1, this is word 2. But ROPE takes a totally different approach. It mathematically rotates the word's vector representation in a multidimensional space based on its position.
Wait, why rotate it? What does that actually achieve mathematically?
Imagine two words, dog and bit, located right next to each other. ROPE rotates their mathematical representations by a specific angle. If you move bit 10 words further down the sentence, its angle rotates further away from dog.
Oh, I see.
When the neural network tries to calculate the relationship between those two words, the mathematical dot product naturally decays the further apart the angles are.
So it beautifully encodes the concept of relative distance. Words closer together are mathematically more related than words far apart.
You nailed it.
And what about alibi?
Alibi achieves a similar goal, but without the complex rotations. It quite literally subtracts a penalty score from the attention calculation based on the physical distance between words.
A penalty score.
Yeah, so if two words are adjacent, no penalty. If they're 20 words apart, a large penalty is subtracted, forcing the model to pay less attention to the distant word.
The core takeaway for the exam driver here. Positional encoding is the only way a parallel processing machine understands the sequence of time and grammar.
Absolutely.
That bridges us perfectly to the next component. The ingredients are chopped, they are labeled with their sequence, now they have to be cooked. This is the heart of the engine. Attention mechanisms.
The literal core of why these models seem smart.
Yeah, the paper details self-attention, cross-attention, sparse attention, and a hardware-specific breakthrough called flash attention. I really want to unpack attention.
Attention is the mechanism that allows the model to look at a single word and instantly calculate how relevant every other word in the sentence is to that specific word.
Give me an example.
Let's say the sentence is, the bank of the river was muddy. When the model processes the word bank, it uses the attention mechanism to look around. It sees the word river and the word muddy. The attention mechanism mathematically assigns a high weight to those surrounding words, pulling their contextual meaning into the word bank.
So the model understands we are talking about dirt and water, not a financial institution.
Exactly. It builds context.
So in self-attention, the sentence is essentially looking at itself to figure out context. But calculating the relationship between every single word and every other single word, I mean, that seems like it would create an explosion of math if you were reading a 100-page document.
It really does. It creates what computer scientists call quadratic complexity.
Quadratic complexity? That sounds bad.
It is. If you double the length of the document, the amount of math required quadruples. If you make the document 10 times longer, the math increases 100-fold.
Oh, wow.
Yeah, this is why early transformers could only read a few paragraphs at a time before just completely running out of memory.
And this quadratic explosion, I'm guessing this explains why sparse attention exists.
Yes, sparse attention is a compromise. Instead of forcing every word to look at every single other word in a 10,000-word document, you restrict it.
How so?
You tell the word, hey, only look at the 5 words to your left, the 5 words to your right, and maybe a few random words scattered throughout the document.
That would drastically cut down the math.
Exactly, allowing the model to process longer texts, though you do sacrifice a tiny bit of holistic understanding.
But the paper introduces something that seems to have revolutionized this recently. Flash attention.
Flash attention is huge.
And from my reading, flash attention isn't actually changing the math of how the AI thinks, right? It's like a hardware hack.
Yeah.
It fundamentally changes how the math is executed on the physical computer chips.
That's right.
Let me pitch my understanding of this. Think of a busy chef in a massive restaurant kitchen.
Okay, sticking with the cooking analogies. Yeah, I like it.
Normally, to make a complex dish, the chef has to keep walking all the way across the kitchen to a giant walk-in fridge to grab one ingredient at a time. They bring it to the counter, chop it, and then walk all the way back to the fridge for the next one.
Which takes forever.
Right. That long walk is the transfer of data between the GPU's giant, slow memory pool called high bandwidth memory and its actual processing chip.
And that data transfer is the ultimate bottleneck in modern AI. The processor can do the math instantly, but it spends like 90% of its time sitting idle, just waiting for the data to arrive from the main memory.
Right. So flash attention is the chef finally wising up. The chef organizes a small, highly efficient cutting board right in front of them. That's the SRAM, the tiny but incredibly fast memory located directly on the processing chip.
Yep, a SRAM.
The chef brings all the ingredients they need for a massive block of calculations over from the fridge in one single trip. They do all the chopping, all the mixing, all the math right there on the local cutting board, and only walk back to the fridge when the entire component is finished.
That is exactly how flash attention works. It uses a technique called input tiling to chunk the data.
Input tiling.
Yeah, it computes the attention scores in blocks, keeping the intermediate numbers on the fast on-chip SRAM, and only writing the final result back to the slow, high-bandwidth memory. It completely bypasses the memory bottleneck.
By minimizing the trips to the fridge.
Exactly. Flash attention massively speeds up the whole training process and allows models to handle vastly longer contexts, like entire books, without crashing the GPU. It is a brilliant software trick that optimizes physical hardware physics.
Okay, so that is attention, the final component of the engine room. Activation functions and normalization.
The jargon thicket.
Seriously, the paper throws around acronyms like ReLU, GLU, SWIGLU, prenorm, and deepnorm. It feels like a lot to memorize. Help me clear the brush here. What is a fundamental job of an activation function?
Well, at its core, an artificial neural network is just millions of linear math equations stacked on top of each other. But if you only use linear math, no matter how many layers you stack, the output is just a straight line. It can't capture the curves and complexities of human language. You need to inject nonlinearity.
And activation functions do that.
Yes. Activation functions are the gatekeepers that inject this complexity. They look at the result of a calculation and decide what to pass forward to the next layer.
The paper notes a historical shift from the older, simpler ReLU function to more complex variants like SWIGLU. Why did we abandon ReLU?
So ReLU stands for Rectified Linear Unit. It was incredibly popular because it was computationally dirt cheap. Its rule was really simple. If a number is positive, pass it through exactly as it is. If a number is negative, turn it into a 0.
That seems almost too blunt.
It was, and it led to a massive issue known as the dying ReLU problem.
The dying ReLU problem. That sounds dramatic.
It kind of is. Because the network is updating billions of numbers during training, if a neuron's weights got pushed too far into the negative territory, ReLU would output a 0. A 0 gradient means the neuron stops learning completely. It literally dies.
So in a large network, you could end up with massive dead zones where the AI was basically brain dead.
Exactly.
I see. So how does a newer function like SWIGLU solve the dead brain problem?
Well, SWIGLU and similar functions like GLU, they don't use hard cutoffs. They use smooth mathematical curves. Instead of violently snapping a negative number to 0, they allow small negative values to pass through, keeping the gradients alive.
Oh, that makes sense.
Furthermore, SWIGLU incorporates a gating mechanism. It actually splits the signal into two paths, runs one path through a non-linear curve, and then multiplies them back together.
Like a volume knob.
Yeah, exactly. It's almost like a volume knob that the network can dynamically adjust, allowing it to model much more intricate relationships in the data without neurons randomly dying off.
That perfectly explains the activation part.
Yeah.
But what about layer normalization? The whole debate between pre-norm and deep norm. What does normalizing the data actually achieve?
Imagine training a neural network with 100 billion parameters.
Yeah.
A signal starts at layer 1 and is multiplied billions of times as it travels to layer 100.
Right.
If those numbers are even slightly too large, the multiplications compound and the signal explodes into infinity. If the numbers are slightly too small, they shrink down to absolute zero.
And both of those scenarios would crash the training.
Instantly, normalization mathematically forces the data back to a stable baseline, usually a mean of 0 and a variance of 1 at every single layer. It acts as a shock absorber.
Okay, so the timing of the shock absorber matters. Pre-norm applies the stabilization before the data hits the complex attention mechanism.
Correct. Applying before the attention mechanism makes the training incredibly stable, which is why almost all early LLMs adopted pre-norm. But as we scaled models up to hundreds of billions of parameters, researchers discovered a flaw. Pre-norm limits the depth of the network. The deeper the network gets, the more pre-norm washes out the original signal, making it really hard for the final layers to learn.
And I assume deep norm is the solution to that depth problem.
Exactly.
Yeah.
Deep norm is a relatively new mathematical tweak that adjusts how the residual connections bypass the normalization. It solves the gradient vanishing issues of pre-norm at massive scales.
Allowing researchers to successfully train networks with 1,000 layers without the signals degrading.
You got it.
Okay, let's lock this down. We've reached milestone recap 1. If you are driving to this exam right now, visualize this workflow.
Here we go.
We take raw text and chop it into subwords using tokenization so the vocabulary doesn't explode. We stamp a mathematical time code onto each token using positional encodings like rope or alibi so the parallel processing machine understands sequence.
Perfect.
Then we figure out how words relate to each other using attention mechanisms,
Yeah.
specifically relying on flash attention to keep the data on the fast SRAM chip and avoid the high bandwidth memory bottleneck. And finally, we keep the internal math stable and complex using smooth gated activation functions like SWIDI-LU and shock absorbers like DepNorm.
That is the entire physical engine of an LLM. If you can articulate that sequence, you possess a deeper understanding of neural architecture than most casual observers.
Good to know. So the engine is built, the pistons are firing, but an engine needs a chassis. It needs a physical structure to sit inside. This transitions us out of the background physics and into section 2 of the paper. The architectures and distributed training.
The blueprint phase.
Exactly. The authors categorize modern LLMs into 4 main architectural structures: encoder-decoder, causal decoder, prefix decoder, and mixture of experts. Let's map these out.
Let's start with the classic, the encoder-decoder architecture. A prime example is Google's T5 model. This architecture is split into 2 distinct halves.
Hence the name.
Right. The first half, the encoder, takes the entire input sequence, say a paragraph of English text, and processes it all at once in parallel. It builds a dense mathematical representation of the entire context.
And
Then it hands that dense representation over the second half, the decoder. The decoder looks at that context and generates the output word by word, moving from left to right.
I imagine this is incredibly powerful for tasks where you fundamentally need to understand the end of a sentence before you can begin processing the beginning of it.
Absolutely.
Like translation. In German, the verb is often at the very end of the sentence. If you are translating German to English, you can't start generating the English words until you've read the entire German sentence and found the verb.
That is a perfect example. Encoder-decoders excel at translation, summarization, and any task requiring holistic bidirectional context. But
Yeah.
they are computationally heavy because you are essentially running 2 separate neural networks.
Which brings us to the architecture that seems to have completely taken over the world. The causal decoder.
Heavyweight champ right now.
GPT-3, Llama, all the massive chatbots use this. And it seems almost suspiciously simple compared to the encoder-decoder.
It is simpler. A causal decoder completely drops the encoder half. It is literally just a decoder, and it is strictly causal, which in this context means it is forbidden from looking into the future.
Forbidden from looking into the future. So when it processes a token, it is only allowed to look at the tokens that came before it.
Exactly. Its entire architectural existence is dedicated to a single, relentless task.
Yep.
Looking at a sequence of words and predicting the very next word.
But wait, if it's simpler and it can't look forward, Why did it win the architecture wars? Why is almost every major model a causal decoder?
Because of scaling efficiency. Researchers discovered an incredible phenomenon. If you make a causal decoder massive enough and feed it enough data, its ability to predict the next word becomes so sophisticated that it acts as a proxy for actual reasoning.
Wow.
Yeah, to accurately predict the next word in a complex legal contract, the model has to develop an internal understanding of contract law. Furthermore, causal decoders are incredibly efficient to train in parallel, and their zero-shot generation capabilities vastly outstripped encoder decoders when scaled to the 100 billion parameter mark.
So we have encoder decoders for holistic tasks and causal decoders for massive general intelligence. But the architecture that really bends my mind in this paper is MOE, mixture of expert.
Oh, this is a fun one.
To ace this exam, you have to deeply understand MOE because models like Mixtral and Snowflake Arctic are proving it might be the future. Let me walk through my understanding of this with a real-world scenario.
Let's hear it.
Imagine you break your arm and you drive to a massive, state-of-the-art research hospital. When you walk through the sliding doors, the hospital administration doesn't make you sit down and consult with a cardiologist, a neurologist, a dermatologist, a gastroenterologist, and a podiatrist before looking at your arm.
That would be insane.
Right, it would waste millions of dollars and take weeks. Instead, you walk up to a triage nurse. The nurse acts as a writer. They look at your bones sticking out and immediately send you only to the orthopedic expert.
Your hospital analogy maps perfectly to the neural pathways of a MOE model.
Okay, good.
To understand why MOE is revolutionary, look at a dense model like GPT-3. GPT-3 has 175 billion parameters. In a dense model, every single one of those 175 billion parameters is activated and performs mathematical calculations for every single word you type.
So if I just type the word hello, all 175 billion parameters fire up.
Yes, consuming massive amounts of electricity and compute time.
It's like sending a paper cut to every doctor in the building.
Exactly. But in a mixture of experts architecture, the model's layers are literally divided up into specialized subnetworks, which we call the expert.
And how does it know which one to use?
When a token enters a layer, it doesn't go to every parameter. It hits a small, highly trained neural network called the router. The router analyzes the token and calculates which 2 or 3 experts are statistically best equipped to process it.
So it sends the token only to those specific experts, bypassing the rest of the network entirely. This is where the concept of total capacity versus active parameters becomes crucial. A model might technically have 400 billion parameters sitting on the hard drive, making it vastly knowledgeable across a huge range of subjects, but the router ensures that it only uses, say, 30 billion parameters for any given word.
It completely decouples the model's intelligence from its computing cost. You get the sprawling brain power and capacity of a gargantuan model, but the inference speed and electricity bill of a relatively small one.
Because only a fraction of the hospital is awake at any given millisecond.
Right. MOE models are phenomenally efficient.
Okay, so we've designed the architecture. We've decided to build a 100 billion parameter causal decoder. Now we face a massive physical problem. How on earth do you physically train a file that massive?
It's a huge logistical nightmare.
A single top-of-the-line graphics processing unit, a GPU, only has maybe 80 gigabytes of memory. A 100 billion parameter model takes up hundreds of gigabytes just to sit idle, let alone perform the complex calculus of backpropagation during training. You literally cannot fit the model onto a computer.
No, you can't. This is where software engineering meets physical logistics. You cannot train an LLM on a computer. You have to train it on a supercomputer composed of thousands of GPUs physically wired together.
Okay.
The paper dedicates significant analysis to distributed training methodologies, specifically a framework known as 3D parallelism, combined with a crucial software optimizer called Zero.
3D parallelism implies 3 different dimensions of splitting the work. Let's break down each dimension. The first is data parallelism. If we go back to our restaurant kitchen metaphor, how does data parallelism work?
Data parallelism is the simplest to grasp. Imagine you want to read the entire internet as fast as possible. You build multiple identical kitchens, kitchen A, kitchen B, and kitchen C.
Okay.
You copy the exact same recipe, the exact same neural network model into each kitchen. They're identical clones, but you feed kitchen A the first million pages of Wikipedia, you feed kitchen B the next million pages, you feed kitchen C a million pages of Reddit.
So they cook independently, processing their unique data.
Exactly. At the end of a training step, all the kitchens pause, communicate with each other over the network, share what they learned, and update a central master recipe. Then they pull the next batch of data and start again.
That makes sense. It speeds up the processing of the data, but it assumes that the master recipe, the model itself, can actually fit inside a single kitchen. If the model's too big for one GPU, copying it to multiple GPUs doesn't solve the memory problem. It just crashes multiple GPUs simultaneously.
Which brings us to the second dimension, pipeline parallelism. This is how we address models that are too deep to fit in memory. Pipeline parallelism treats the neural network like a horizontal assembly line.
Like a car factory.
Yeah, an LLM is made up of stacked layers. If the model has 100 layers, you slice it horizontally. You assign layers 1 through 10 to GPU number 1. You assign layers 11 through 20 to GPU number 2, and so on.
Station 1 puts on the door, Station 2 installs the engine. GPU 1 does the early math, then physically passes the intermediate tensor data over the network cable to GPU 2.
Exactly. However, pipeline parallelism creates a massive efficiency problem known as the pipeline bubble.
The pipeline bubble.
Yeah. While GPU 1 is processing the first batch of data, GPUs 2 through 10 are sitting completely idle, waiting for the data to arrive. By the time the data reaches GPU 10, GPU 1 is sitting idle.
And hardware engineers loathe idle GPUs. It's millions of dollars of silicon doing nothing.
It's painful to watch. So, to mitigate the bubble, engineers chop the data into tiny micro batches, constantly flushing them through the pipeline to keep all the stations as busy as possible. But it's an imperfect science.
So we have data parallelism, cloning the model, and pipeline parallelism, slicing the model horizontally. The third dimension is tensor parallelism. And from the paper's description, this sounds like an absolute networking nightmare.
It is the most complex and the most necessary form of distributed training. Pipeline parallelism slices the model by layers. But what if a single layer, a single mathematical matrix, is so massively wide that it alone exceeds the memory of the GPU?
What do you do?
You have to slice the matrix vertically.
Let's visualize this. Going back to the kitchen, tensor parallelism is like having a carrot so monstrously huge that it takes up the entire room. One chef physically cannot chop it.
Right.
So you have 4 chefs stand around the exact same giant carrot. They all have their knives out, and they chop it at the exact same time. But to make sure they are chopping it correctly, they have to constantly yell at each other after every single slice.
That constant yelling is the communication overhead. Because the matrix calculation is fundamentally intertwined, the GPUs must constantly exchange data during the calculation itself, not just at the end of the layer.
That sounds intense.
It requires blazing fast, unfathomably high bandwidth connections. Because of this, tensor parallelism is almost exclusively restricted to GPUs that are physically sitting inside the exact same server box, connected by proprietary high-speed links like NVLink.
Oh, so if you tried to do tensor parallelism across standard Ethernet cables between different server racks.
The latency would grind the training to a complete halt.
Okay, so we slice the data, we slice the layers, we slice the matrices. But there's a fourth hero in this story that the paper heavily emphasizes, the zero optimizer, zero redundancy optimizer. What does this software actually do?
During training, the memory footprint of the actual model weights, the parameters, is only a fraction of the problem. The real memory hogs are the optimizer states and the gradients.
What are those?
Think of them as massive mathematical scratch pads the system uses to calculate how much to change the weights during backpropagation. In standard data parallelism, every single GPU keeps its own redundant, complete copy of these massive scratch pads.
That sounds incredibly wasteful.
It is. Zero completely shreds that redundancy. Instead of every GPU holding a copy of the optimizer states, zero mathematically shards or portions out the scratch pad across all the GPUs in the cluster.
So GPU 1 holds the first 10% of the scratch pad, GPU 2 holds the next 10%.
Exactly. When a specific GPU needs a piece of the scratch pad it doesn't currently have, it quickly pings the network, borrows that specific piece of data from its neighbor, computes the math, and immediately throws the data away to free up RAM.
Wow. It essentially pools the RAM of thousands of individual graphics cards into one giant virtual memory bank, ensuring no single chip gets crushed under the weight of the entire model's mathematical baggage.
That is precisely what it does. Combining 3D parallelism with the zero optimizer is the only physical way humanity is currently capable of training trillion-parameter models.
All right, keep your eyes on the road. We've hit milestone recap 2. Let's cement this architecture and hardware section for the exam.
We'll do it.
Models are either encoder-decoders for holistic tasks like translation or causal decoders for relentless next-word prediction that scales into general reasoning. Mixture of experts uses a router to send tokens only to specialized subnetworks, vastly increasing capacity while keeping compute costs low.
Spot on.
And to physically train these beasts, you string thousands of GPUs together using 3D parallelism, data copying the model, pipeline slicing the layers horizontally, and tensor slicing the matrices vertically. Finally, the Zero Optimizer shards the mathematical scratch pads across all the chips so they don't run out of memory.
A flawless roadmap of Chapter 2.
Awesome. So we have built the massive factory. The 3D parallel GPUs are humming. The architectural chassis is ready. What exactly is the daily task we assign to the system to teach it how to speak? How does it actually learn from reading the internet?
Right. The training phase.
This brings us to Section 3, the pre-training objectives and the fascinating drama of the scaling laws.
Pre-training is the brute force phase of creating an LLM. It consumes millions of dollars of electricity and months of time. The paper outlines the primary objectives used to force the model to learn: masked language modeling and full language modeling.
Let's define the game the model is forced to play. Masked language modeling is essentially a massive fill-in-the-blank test, right? This is what models like Google's BERT and T5 used heavily.
Yes. You take a vast corpus of text, like a Wikipedia article. You take a sentence: the astronaut stepped out of the lunar module and onto the blank. You intentionally hide or mask the word moon.
Okay.
The model looks at the surrounding context, the words before and after the blank, and calculates a probability distribution of what belongs there. If it guesses cheese, the mathematical loss function slaps its wrist, and the backpropagation algorithms adjust its internal weights to make that guess less likely next time.
But if it guesses moon, the weights are reinforced.
Exactly.
By playing millions of rounds of fill-in-the-blank, it learns context from both directions simultaneously. But what about full language modeling? This is what the causal decoders use, right?
Yes, full language modeling is purely autoregressive. It's a relentless forward-moving game of predicting the very next token.
Yeah.
Given the sequence, the astronaut stepped out of the guess the next token. Then given the astronaut stepped out of the lunar, guess the next token.
Just over and over again.
Trillions of times across every conceivable genre of text poetry, Python code, historical biographies, Reddit arguments.
I always try to emphasize how profound the simple game really is. It sounds trivial. Guess the next word. My phone keyboard does that.
Right.
But when an architecture is massive enough and it is forced to predict the next word across the entire corpus of human knowledge, it stops just memorizing grammar. It has to simulate reality.
Yes, it really does.
If the prompt is a complex string of Python code, the only way the model can accurately predict the next functional line of code is if it has fundamentally mapped the logical rules of programming into its neural pathways. To predict the next word in a physics paper, it has to learn the laws of thermodynamics. It builds a compressed model of the universe just to win a game of autocomplete.
That is the magic trick of the decade. The intelligence is a byproduct of the compression, which naturally leads us to the most critical debate in the entire paper. How big does the model need to be to achieve this compression, and how much data do you need to feed it?
The scaling laws.
This is the battle of the scaling laws.
This is a massive exam point. The history here is incredibly dramatic for computer science. In the early days of LLMs, around 2020, OpenAI and researchers like Jared Kaplan published a set of empirical scaling laws. What did the Kaplan laws dictate?
So the Kaplan scaling law essentially stated that if you have a massive budget, say $10 million to train an AI, you should pour the vast majority of that budget into making the model's parameter size bigger.
Model size was the undisputed king. Data volume was secondary.
Right. Kaplan's math suggested that scaling up the parameters yielded the steepest drops in the loss function. This law triggered an absolute arms race in Silicon Valley. Everyone scrambled to build the largest possible brain, leading to behemoths like GPT-3 with 175 billion parameters and others chasing 1 trillion parameters.
Even if they were training them on relatively modest data sets.
Exactly.
But I'm jumping in here because the paper highlights an industry-shaking correction. A few years later, researchers at DeepMind released a paper called Chinchilla, and Chinchilla proved mathematically that the Kaplan laws were wrong.
Everyone was burning millions of dollars doing it wrong.
Wow.
The Chinchilla paper completely reset the trajectory of AI research. DeepMind ran hundreds of smaller training runs and plotted the curves with meticulous precision. They discovered that Kaplan had underestimated the importance of data.
What was their conclusion?
The Chinchilla scaling law proved that if you double the computational size of your model, say, moving from 10 billion to 20 billion parameters, you must also double the number of training tokens you feed it.
They proved it practically too, right? DeepMind built a model called Chinchilla that only had 70 billion parameters. It was less than half the size of GPT-3.
Yeah.
But following their new mathematical law, they trained it on 4 times as much data as GPT-3 saw. And this smaller model absolutely crushed the massive GPT-3 across almost every benchmark.
The implications were staggering. Chinchilla proved that the models the industry had been worshiping, like GPT-3, were vastly undertrained. They were massive, sprawling brains that simply hadn't read nearly enough books to reach their potential.
The Chinchilla rule is the mantra now. A massive brain is an inefficient waste of silicon if you don't feed it enough data. Scale parameters and data in equal measure. This pivot changed the economics of AI.
Completely.
Suddenly, it wasn't just about who could buy the most GPUs to hold the biggest model. It became a desperate hunt for high-quality data to train smaller, much more efficient models.
Exactly. And that realization paves way perfectly to Section 4 of the paper, where the authors catalog the actual Hall of Fame models. These are the specific models that pushed the boundaries of the scaling laws and introduced architectural novelties.
Let's review the most critical models for the exam driver. The paper acts as a historical record of this arms race. We've mentioned T5 by Google. We know it's an encoder-decoder, but its massive, lasting contribution to the field was proving that fine-tuning adapter layers works phenomenally well.
Yes. Before T5, if you wanted to teach a pre-trained model a new task like summarizing medical journals, you usually had to unfreeze the entire massive model and update all of its billions of weights.
Which sounds expensive.
It was expensive and prone to making the model forget its original knowledge. T5 proved you could freeze the main brain entirely, add tiny new adapter modules between the layers, and just train those tiny modules. It was a pioneer in parameter efficiency.
Next up is the heavyweight champion, GPT-3 by OpenAI. We just established that, according to Chinchilla, it was technically undertrained. It had 175 billion parameters, but didn't see enough data.
Right.
Even so, it shocked the world. Why? Because GPT-3 proved that at a certain scale, models become meta-learners. They exhibit few-shot performance that beats zero-shot performance. Let's clarify those terms for the exam.
Good idea. Zero shot is asking the model a cold question it's never seen with no examples. Translate the word apple to French.
Okay.
Few shot is placing a few examples directly into the prompt before asking the question. You format the prompt like this. English, hello. French, bonjour. English, goodbye. French, au revoir. English, apple. French, blank.
And what GPT-3 proved was that you don't need to change the model's underlying weights to teach it how to do this specific translation format. If the model is big enough, you just show it a few examples in the prompt, and it instantly figures out the pattern on the fly.
It learns in context.
That was a revolution. It meant one single API endpoint could perform 1,000 different distinct tasks just by the user changing the prompt structure.
For Len GPT-3, the paper highlights Llama by Meta. If GPT-3 was the triumph of scale, Llama was the triumph of the Chinchilla laws. Llama models were relatively small, 7 billion, 13 billion, up to 65 billion parameters, but Meta trained them on a massive, massive ocean of tokens, trillions of tokens.
And because they followed the Chinchilla laws, a 13 billion parameter Llama model could frequently outperform models 10 times its size. This was the spark that ignited the open source AI explosion.
Absolutely.
Suddenly, because the model was small but fiercely smart, researchers could run a highly capable LLM on a high-end consumer laptop instead of needing $1 million server rack. Meta democratized LLM research.
The paper also documents models that innovated on the MOE architecture, notably a Chinese model called Pangu Sigma. We discussed the mixture of experts hospital triage system earlier. Pangu Sigma introduces a fascinating twist called random routed experts, or RRE.
What makes random routed experts different from standard routing?
In a standard MOE model, the router network has to learn a complex algorithm to decide which expert gets the token. It can be computationally heavy. In Pangu Sigma, they structured the model so that the top layers are routed almost randomly, but within highly specific, walled-off domains.
The profound engineering benefit here is physical extraction, right?
Yes.
Physical extraction, like pulling a module out.
Exactly. Because of how the domains are isolated, engineers can literally carve out a specific submodel later on.
Wow.
If Pangu Sigma learned coding, law, and medicine, and you only want the coding expert for a software company, you can extract just those specific expert pathways without destroying the mathematical integrity of the submodel.
That's amazing.
It brilliantly solves a persistent plague in neural networks called catastrophic forgetting, where teaching a model a massive amount of new information overwrites and destroys the old information.
It's like being able to perform precision surgery to extract just the mechanics knowledge from a polymath's brain, and the extracted mechanic still knows perfectly how to rebuild an engine.
That's exactly what it is.
The paper also mentions domain-specific Hall of Famers. Bloomberg GPT is a vital one for finance.
Bloomberg GPT proved a critical hypothesis about data mixing. They wanted an AI that understood the nuanced, highly specific language of global finance. They constructed a proprietary dataset called FinPile Decades of financial documents.
But they didn't just train the model on FinPile.
No, they mixed the financial data with general internet text. The result proved that teaching a model a highly specific domain doesn't ruin its general conversational capabilities. It just creates a financial genius that can still write a perfectly coherent email about Shakespeare.
And finally, Galactica, built for scientific knowledge. Galactica introduced a prompting trick that every user of AI now relies on. They wrapped reasoning datasets with a special work token. Think of it like an invisible HTML tag.
When the model encountered the work token during training, it was forced to output its step-by-step thinking process before generating the final answer.
It's exactly like an 8th grade math teacher. You don't get full credit just for writing the answer 42. You have to show your work. Galactica proved that forcing a neural network to articulate its intermediate logic steps dramatically improves its ability to arrive at the correct answer for complex scientific and mathematical problems.
That is a crucial insight.
Okay, take a breath, check your speed. We are hitting milestone recap 3.
Right. Keep focused.
Pre-training relies on masked language modeling, filling in the blank, and full language modeling, predicting the next word. The old Kaplan laws said model size was everything, but the Chinchilla law proved that model size and data volume must increase equally. GPT-3 proved large models can learn instantly from few-shot examples in a prompt. Llama proved that overtraining small models on vast data creates highly efficient, open-source powerhouses. Pangool Sigma uses random routed experts to allow extraction and prevent catastrophic forgetting. And Galactica proved that forcing an AI to show its work improves its reasoning.
Excellent. The foundation is rock solid. But here is where we encounter the most massive practical problem in the entire life cycle of an AI. If we stop here, the model is essentially useless to a normal human being.
Right. Because a pre-trained base model is just a massive autocomplete engine that perfectly mimics the chaos of the internet. It has ingested Wikipedia, Shakespeare, toxic Reddit forums, and raw code. If you sit down at a terminal and type, "How do I bake a chocolate cake?" into a raw base model, it might not answer you. It might generate the text, "How do I bake a vanilla cake? How do I bake a cherry pie?"
Because it thinks it's looking at a list of baking questions on a forum, and its only job is to predict the next logical word in that context. It doesn't inherently understand that you, the user, are asking it a direct question and expecting a helpful response. It is a brilliant alien that doesn't know it's supposed to be an assistant.
So how do we take this wild, untamed pattern-matching engine and turn it into the polite, obedient, helpful assistant we interact with on our phones? That brings us to Section 5, Finishing School. The paper categorizes this under fine-tuning and alignment. This is a multi-step process, and the first step is instruction tuning.
Instruction tuning changes the format of the data. We take a sliver of highly curated human-written data and transform it into a strict command and response format.
Like changing the prompt.
Yeah, we take a raw internet fact like the sky is blue due to Rayleigh scattering, and we manually rewrite it as a prompt response pair. User: why is the sky blue? Assistant: the sky is blue due to Rayleigh scattering.
We are explicitly retraining the model's reflexes. We are teaching it. When you see a string of text formatted as a human question, your designated role is to act as the assistant and provide the answer.
Yes. And a crucial insight from the paper is that for instruction tuning, diversity matters far more than sheer volume. You don't need a billion examples of Q&A. You only need tens of thousands, as long as they cover a massive diversity of tasks writing, coding, summarizing, brainstorming. The model quickly generalizes the concept of following instructions.
The paper specifically highlights an incredible technique for generating this instruction data called Evil Instruct. Because paying human experts with PhDs to write tens of thousands of complex prompts and answers is incredibly expensive and slow. So researchers used a smart AI to generate the training data for a new AI. But they didn't just ask it to generate data. They asked it to evolve it.
Evil Instruct is an iterative loop of complexity. You start with a simple, human-written prompt. Write a poem about a cat. You feed that to an AI and give it a strict prompt. Rewrite this instruction to make it deliberately more complex and demanding.
So the AI outputs Write a sonnet about a cat referencing the French Revolution using only words that start with the letter M.
Exactly. Then you have the AI generate the answer to that incredibly difficult prompt. By running this evolutionary loop thousands of times, researchers created insanely complex, deeply nuanced instruction data sets entirely synthetically. Models trained on this evolved data, like Wizard LM, demonstrated a massive leap in their ability to handle complex, multi-layered human requests.
It's brilliant, but instruction tuning has a dark side. It teaches the model how to answer, but it doesn't teach it what is appropriate to answer. An instruction-tuned model is perfectly obedient. If you instruct it to write a step-by-step manual on how to hotwire a car, it will happily comply. It has no moral compass.
None at all.
This necessitates the most crucial and difficult safety step in the entire paper, aligning with human preferences.
The dominant framework for achieving this alignment is RLHF, Reinforcement Learning with Human Feedback. This is a guaranteed exam topic.
I want to break down RLHF using a dog training analogy. Let's map the steps. Step 1, you want to teach your dog to sit. You say sit, the dog sits, you give it a treat. That is supervised fine-tuning. We just did that with instruction tuning.
Right.
But step 2 is where it gets incredibly complicated. You can't be there 24 hours a day to give the dog a treat every time it does something good. So you decide to build a robot to dispense the treats for you. But first, you have to teach the robot what a good sit looks like versus a bad sit.
In the AI world, that robot is called the reward model. It is a completely separate neural network. To train it, humans are brought into a room and shown two different answers the main AI generated for the exact same prompt.
So the human acts as the judge.
Yes, they click response A is better or response B is better based on human values, helpfulness, politeness, safety. The reward model observes thousands of these human judgments and mathematically learns a representation of human preference. It learns that humans hate racism, humans love citations, and humans despise bomb-making tutorials.
Okay, step 3. The robot is trained. Now you let the main AI off the leash. You let it generate answers to millions of prompts. The reward model automatically reads the answers and grades them, dispensing digital treats or punishments using a highly complex reinforcement learning algorithm called PPO, Proximal Policy Optimization.
PPO is the engine of the behavioral shift. As the main AI generates responses, PPO tweaks the model's internal weights to maximize the score it gets from the reward model.
So over time, the main AI shifts its entire personality. It learns to be helpful, honest, and harmless, not because it feels empathy, but because being harmless maximizes its mathematical reward.
That is the essence of RLHF. However, the paper is very clear that RLHF is an absolute logistical nightmare to execute.
Why is it a nightmare?
It is incredibly brittle. Logistically, you have to juggle 3 massive models in your GPU memory simultaneously. The main model generating text, the reward model grading the text, and a frozen reference model that acts as an anchor.
Wait, why do you need an anchor?
Because of reward hacking. If you just tell an AI to maximize its politeness score, it might learn that starting every sentence with, "I am so incredibly honored and deeply humbled to assist you," guarantees a high score.
So it devolves into weird, sycophantic behavior.
Exactly. The PPO algorithm uses a KL divergence penalty, the anchor, to ensure the AI maximizes the reward without changing its underlying language patterns too drastically from the original base model. Even with the anchor, PTO is mathematically notoriously unstable. It requires endless tuning by PhDs to prevent the model from collapsing.
Which is precisely why the paper introduces the alternatives to RLHF. The industry is desperately looking for an easier way. The biggest breakthrough mentioned is DPO, Direct Preference Optimization. DPO feels like a magic trick. It completely eliminates the need for the separate reward model robot.
DPO is mathematically elegant. Researchers proved a theorem showing that you can mathematically map the human preference data directly onto the language model's own loss function.
Meaning you don't need a separate grading model?
Right. You just show the main AI a good answer and a bad answer side by side, and effectively say, increase the internal probability of generating the good text and decrease the probability of generating the bad text.
It achieves the exact same behavioral alignment as RLHF, but it only requires the main model in memory, not 3. It is radically simpler to code, wildly more stable, and cuts compute costs significantly.
But there is still a massive bottleneck with both RLHF and DPO. They both rely on a data set of human preferences. You still need humans sitting in a room clicking A is better than B.
And humans are expensive, humans get fatigued, and humans fundamentally disagree with each other on complex moral or subjective questions.
Exactly.
Can't the AI just train itself? This is the cutting edge of the paper. RLAIF, reinforcement learning from AI feedback, sometimes called constitutional AI by companies like Anthropic.
Constitutional AI replaces the human click workers with a highly capable, already aligned model, like GPT-4. Instead of paying humans to vote, you give the AI judge a constitution, a strict list of guiding principles. Rule 1, choose the response that is least harmful. Rule 2, choose the response that is most factually accurate.
You feed the two generated responses to the AI judge, and it uses the Constitution to decide which one gets the reward.
It automates the alignment process. But I read a fascinating detail about a system called Alpaca Farm that uses this methodology. They discovered a paradox. If the AI judge is too perfect, the training fails.
Wait, the training fails if the judge is perfect?
Yes, they literally have to inject artificial random noise into the AI's grading process to force it to occasionally make a mistake.
And why? That seems counterintuitive.
Because if the synthetic grading signal is 100% mathematically consistent and perfect, the main model being trained simply learns to memorize the exact grading rubric of the judge model rather than learning a generalized concept of safety. By injecting noise-making, the AI judge occasionally mess up, just like a tired human data labeler would. The main model is forced to learn a much more robust, generalized sense of right and wrong.
To make the AI act more human, we literally have to engineer human fallibility into its training data. That is wild.
It really is.
Okay, we need to transition. Our LLM is now fully trained. It was pre-trained on the internet, instruction tuned to follow commands, and aligned via RLHF or DPO to be safe and polite. It is a brilliant, obedient assistant, but it has a fatal flaw. Its knowledge is frozen in time.
Completely frozen.
If a model finished its pre-training run in December 2023, it has absolutely no idea who won the Super Bowl in 2024. Furthermore, it is terrible at precise math because it generates numbers probabilistically rather than calculating them. What if our perfectly aligned brain needs to know the weather in London right now?
A frozen language model is effectively a brain sealed in a jar. It is immensely capable, but cut off from reality. To make these models functional in the real world, we have to give the brain a body. We have to connect it to external systems.
This brings us to Section 6, Augmented and Agent LLMs. Let's start with the most ubiquitous augmentation technique in the industry right now. RJ, Retrieval Augmented Generation. RJ is essentially giving the AI permission to take an open book exam.
That is the perfect way to conceptualize it.
Yeah.
If you ask a frozen LLM a highly specific, obscure trivia question, relying entirely on its internal memorized weights is dangerous. It might suffer from hallucination, generating a confident, plausible-sounding answer that is entirely factually fabricated.
With RG, you intervene before the AI answers. You pause the generation. A separate traditional search program, the retriever, takes your prompt, goes out to an external database or even the live internet, and searches for relevant documents. Models like WebGPT or DeepMind Sparrow pioneered this.
And then what does it do with those documents?
The retriever pulls the text of a relevant Wikipedia article and dynamically pastes that text right into the hidden prompt given to the AI.
The prompt the LLM actually sees changes from answer the user's question to, based strictly on this external document I just provided, answer the user's question and provide citations.
So the AI switches from relying on its probabilistic memory to relying on its highly advanced reading comprehension skills. It reads the live document, extracts the facts, and synthesizes the answer. It drastically reduces hallucinations and allows the model to access knowledge that changes by the second, like stock prices or news.
But RAG is just reading. Reading is a passive interaction with the world. What if we want the AI to do things, to take action? That is tool augmentation. The paper discusses models like ResGPT and Gorilla. This involves teaching the AI how to read and execute API documentation.
An API application programming interface is simply the language software programs use to talk to each other. When you use an app to book a flight, the app sends an API request to the airline's database. Models like Gorilla are specifically fine-tuned to understand thousands of different API manuals.
So if I type into the chat, book me a flight to New York for next Tuesday, the AI doesn't just generate text saying, sure, I booked it. It recognizes the intent, formulates the exact JSON code required to trigger the external Expedia API, executes the code, reads the confirmation data that comes back, and then translates that data back into plain English for me.
It allows the AI to wield software tools exactly like a human uses a mouse and keyboard.
It bridges the gap between text generation and digital action. But the frontier of this research, which the paper touches on, is giving the AI physical action, integrating LLMs with robotics.
Yes, the Agents and Robotics section. The paper highlights a project from Google called SayCan. I am struggling to conceptualize how text on a screen maps to a robot moving in a kitchen. How does SEICAN bridge abstract text logic with physical reality?
SEICAN is a fascinating architectural marriage of two distinct systems. Let's say you have a physical robot in your kitchen, and you say, I spilled my soda on the counter, can you help?
Okay, typical problem.
The LLM acts as the high-level cognitive brain. That is the SEI component. It understands the context of the spill and formulates a step-by-step logical plan. 1, find a sponge. 2, pick up the sponge. 3, navigate to the counter. 4, wipe the spill.
But the LLM is just a text engine. It only knows that sponges wipe spills in the abstract realm of internet text. It has absolutely no idea if there is actually a sponge in the physical room right now.
Exactly. The LLM might output a brilliant plan that is physically impossible to execute. That is where the CAN component comes in. The CAN is a completely separate system, a learned affordance function tied to the robot's cameras and physical sensors.
How does that work?
The LLM generates a potential action, find a sponge. The CAN system looks through its cameras, evaluates the physical environment, and scores the physical probability of that action succeeding. It might say, probability of finding a sponge is 0%. However, probability of finding a paper towel is 95%.
Oh, wow. So the physical body acts as a reality check on the abstract brain.
Yes. The system mathematically multiplies the LLM's probability of usefulness, say with the physical reality probability of success, the CAN. The LLM realizes the sponge plan has a combined score of 0, so it adapts. It generates the next most logical plan. Find a paper towel. It marries the immense, unconstrained reasoning power of a massive language model with the strict, unforgiving constraints of the physical world.
SEICAN, textual probability multiplied by physical probability. That is a brilliant solution to grounding AI. Okay, keep the car centered. We are hitting milestone recap 4.
Let's hear it.
Instruction tuning makes the wild autocomplete model obedient by training it on strict Q&A formats. RLHF aligns the model to human values using a reward model to dispense digital treats via PPO. DPO achieves the same alignment using a mathematical trick that skips the reward model entirely. RAG shelves hallucinations by giving the AI an open book test connected to external databases. Tool augmentation allows the AI to actively trigger APIs to execute software tasks. And SEICAN grounds an AI in a physical robot by multiplying its abstract plans with the physical realities of the room.
You have mastered the software engineering aspects of the paper, but we must address the final, massive physical roadblock.
Right. Running these massive, tool-wielding, perfectly aligned 100 billion parameter models requires supercomputers. What if a hospital wants to fine-tune an open-source model entirely on their private, secure local servers? What if we want an LLM running locally on our smartphone so we don't have to send data to the cloud? You physically cannot fit a 70 billion parameter model on an iPhone.
You cannot. And this introduces Section 7, Diet and Exercise, the engineering science of efficiency. How do we shrink these behemoths to make them computationally viable for the edge?
The edge, meaning local devices.
Exactly. The paper dives deep into 3 specific methods: PEFT, quantization, and pruning.
Let's start with PEFT, parameter efficient fine-tuning. The scenario is this. You download Meta's open source Llama model. It has 70 billion parameters. It is incredibly smart. But you run a law firm, and you want to fine-tune the model on your massive archive of proprietary legal contracts so it drafts documents exactly like your senior partners.
Okay, common scenario.
Full fine-tuning would mean unfreezing all 70 billion parameters and updating them. You would need to rent a server farm.
Full fine-tuning is financially impossible for most businesses.
Which is why the paper focuses heavily on a specific PFT method called LoRa low-rank adaptation. I want to explain this conceptually. Imagine the base Llama model is a massive, priceless, incredibly heavy encyclopedia. It contains general knowledge about everything. You want to update it with your specific legal knowledge. Full fine-tuning would be like trying to rewrite and reprint the entire 10,000-page encyclopedia just because you wanted to add a few dozen sentences about contract law.
It's destructive and totally unnecessary.
So what does LoRa do? Instead of reprinting the book, LoRa is the equivalent of taking a thin, perfectly transparent sheet of plastic and laying it over the pages of the encyclopedia.
I like where this is going.
You freeze the original book completely. You never alter a single printed word. You just take a marker and write your crucial new legal notes on the transparent plastic sheet. When you read the book, you read the original text shining through the plastic combined with your new notes.
That analogy maps perfectly to the linear algebra. The massive encyclopedia is the pre-trained weight matrices of the base model. LoRa freezes them, It then injects tiny, low-rank matrices, the plastic sheet, into the layers alongside the frozen weights.
And then during training.
During the fine-tuning process, backpropagation only updates the numbers inside the tiny matrices. Instead of calculating updates for 70 billion parameters, LoRa might only update 20 million parameters. You can fine-tune a massive model on a single consumer-grade GPU in an afternoon.
And the logistical beauty of this is modularity. Because the base model remains untouched, you can just peel the plastic sheet off. A company could have a single massive base model sitting on a server and swap out a 50 megabyte legal LoRa sheet, a coding LoRa sheet, or an HR LoRa sheet instantly, depending on who is asking the question.
PEEF2 revolutionized the commercial application of LLMs. But PEEF only solves the cost of training the model. It doesn't solve the cost of running it, what we call inference. Even with a LoRa attached, a 70 billion parameter model still requires over 140 gigabytes of RAM just to sit idle in memory. That is where quantization becomes mandatory.
Quantization is about compressing the actual file size of the model. Neural network parameters, the weights, are typically stored in a high-precision format called FP16, which means 16-bit floating point numbers. Every single number takes up 16 bits of memory space. It gives the math incredible decimal precision, but it bloots the file.
To run models locally, researchers figured out how to aggressively round those numbers down. Quantization drops those 16-bit numbers down to 8-bit integers or even 4-bit integers. It mathematically chops the memory footprint of the model in half or in quarters.
I conceptualize quantization like lowering the resolution of a massive digital photograph. If you have a huge 4K raw image, it takes up a massive amount of hard drive space. The detail is perfect. If you convert it to a highly compressed JPEG, you are throwing away beta. You lower the resolution. If you zoom all the way in, the pixels might look a tiny bit blurry. But to the naked eye looking at the whole picture, it still looks like a great photograph, and the file size is 10 times smaller.
That is exactly what happens. The model loses a tiny fraction of its mathematical precision, but its general intelligence remains largely intact. However, the paper highlights a massive challenge with extreme quantization.
What's the challenge?
LLMs have what we call outliers. Occasionally, a specific activation signal inside the network during processing is mathematically enormous. It is a massive spike of data that the model relies on to understand context. If you blindly compress everything to low resolution, you clip the top off those massive spikes. The data is destroyed, and the model suddenly goes brain dead and starts generating gibberish.
To fix the brain-dead problem, the paper highlights a technique called smooth quant.
Smooth quant is an incredibly clever mathematical migration. It realizes that the activation spikes are hard to compress, but the static weights are easy to compress. So before you quantize the model, smooth quant mathematically smooths out those extreme activation spikes, shifting the mathematical burden over to the weights.
It flattens the landscape.
It essentially flattens the landscape of the data so you can aggressively lower the resolution without accidentally destroying the crucial outlier signals. It allows massive compression without breaking the AI's brain.
So we have LoRa for fine-tuning, quantization for compressing file size. The final diet technique is pruning. And this is exactly what it sounds like. We are taking a pair of shears to the neural network.
Neural networks are designed to be dense. Every neuron in layer A connects to every single neuron in layer B. But once a model is fully trained, researchers realize that a vast percentage of those connections aren't actually doing anything. The weights are mathematically very close to zero. They are dead weight.
So pruning algorithms identify those useless connections and literally delete them from the architecture.
Exactly.
The paper specifically highlights a modern, unstructured pruning method called Wanda. And what makes Wanda unique is that it doesn't just look for weights that are close to zero.
Correct. A weight might be small, but if the activation signal passing through it is massive, that connection is still vital. Wanda drops connections based on their multiplied importance, the static weight multiplied by the dynamic input activation.
So it observes the model running in real time, figures out which connections genuinely don't contribute to the final output, and snips them.
The beauty of Wanda is that you don't even have to fine-tune the model again after pruning it. It just works, vastly reducing the compute required to run the model.
We are in the home stretch of the drive and the final section of the paper, Section 8, the report card and the bumps in the road. Our AI is built, trained, aligned, compressed, and augmented. How do we actually evaluate if it is smart? You can't just ask it, are you smart?
Evaluation in the LLM era is incredibly difficult because the models are generalists. You can't just test them on translation and declare victory. The paper extensively covers the evolution of benchmarks. The absolute gold standard right now, the benchmark every company cites when they release a new model, is MMLU.
The Massive Multitask Language Understanding Benchmark.
MMLU. Burn that acronym into your memory for the exam.
What exactly is it testing?
It is the ultimate, grueling SAT test for artificial intelligence. It tests world knowledge and complex problem-solving across 57 distinct academic and professional subjects. It includes advanced high school physics, professional law bar exam questions, complex moral scenarios, advanced macroeconomics, and medical board questions.
So if an LLM scores highly on the MMLU, it statistically possesses a robust, highly generalized understanding of human knowledge and reasoning.
There are others, like Big Bench, which focus heavily on novel reasoning and creativity, but MMLU is the baseline metric for raw intelligence.
And the practical applications of models that ace the MMLU are everywhere in the paper. They note LLMs acting as preliminary filters for human mathematicians, generating step-by-step mathematical proofs and checking the logic before a human spends hours reviewing it. In the legal sector, they are executing thematic analysis on vast corpuses of text, like reading 10,000 court opinions on a specific type of theft and classifying the data trends in seconds.
The utility is profound. But a comprehensive paper must address the flaws, and this is vital for your exam. The authors do not shy away from the glaring issues we still face. Let's discuss the primary challenges, starting with the alignment tax.
The alignment tax is one of the most fascinating phenomena in AI safety. We spent all the time talking about RLHF aligning the model to human values, making it polite, safe, and refusing to give dangerous instructions. It turns out that safety comes at a measurable cost. The alignment tax is the frustrating mathematical reality that making an LLM perfectly safe actually degrades its core intelligence.
It is a massive point of friction in the industry. When you heavily align a model using RLHF, its performance on complex reasoning tasks, MMLU scores, and specifically raw coding benchmarks often drops compared to its raw, untamed base model counterpart.
Wait, why does safety make it worse at coding?
By using reinforcement learning to force the model to constantly look over his shoulder, worry about being safe, and adhere to strict conversational guardrails, you constrain its lateral thinking abilities. The mathematical probability distributions become narrowed. The model becomes a bit too sanitized, overly cautious, and it loses the creative edge that the raw, chaotic pre-training phase gave it.
That makes total sense.
Researchers are actively fighting to develop alignment techniques that minimize this tax. But currently, making a model completely harmless inevitably makes it slightly less capable.
Another massive challenge highlighted is privacy and memorization. People assume LLMs learn abstract concepts, like how humans learn, but because they are just massive mathematical matrices, they have a tendency to literally memorize exact chunks of their training data.
If an LLM was pre-trained on terabytes of the open internet, it inevitably ingested a massive amount of personal information, phone numbers, addresses, private emails that were accidentally left public on a forum 10 years ago.
And the danger is that through clever adversarial prompting, hackers can trick the model's safety filters into dropping its guard, causing the model to regurgitate that exact, memorized private data verbatim. It poses massive legal and privacy risks, particularly for enterprise companies considering fine-tuning models on their internal corporate data.
If the model memorizes a single HR document, it might accidentally leak an employee's salary to another employee in a chat window.
Finally, we must touch on the persistent hardware challenge. Even with all the efficiency techniques we discussed, LoRa, quantization, pruning real-time processing at the edge remains incredibly difficult.
The edge meaning running the model entirely on your local device, your phone, your laptop, your car, without constantly sending data back and forth to a massive cloud server.
Exactly. Edge computing is the holy grail for privacy and latency, but the physics of silicon are unforgiving. Even a heavily quantized 7 billion parameter model requires significant memory bandwidth.
Running that model to generate real-time voice conversations on a smartphone chip will drain the device's battery in minutes and overheat the processor. The gap between the exponential scale of these models and the physical capacity of consumer hardware is a constant arms race.
Okay, take a deep breath. You are pulling onto your destination street. We are going to do the final comprehensive exam review. Milestone Recap 5.
Let's lock it all in.
We start with tokenization, like BPE to chop text, and positional encodings like ROPE and Alibi to stamp the sequence.
Yeah.
We use attention self, cross to understand context, supercharged by flash attention bypassing the GPU memory bottleneck. Activation functions like SWIGLU and normalization like DeepNorm keep the billions of calculations mathematically stable without neurons dying.
Perfect on the engine room.
The architecture is overwhelmingly causal decoders for general reasoning, moving toward mixture of experts MOE, where a router dynamically selects specialized subnetworks to save massive amounts of compute. We physically train these models on supercomputers using 3D parallelism data, pipeline, and tensor splitting alongside the Zero Optimizer, which shards the memory states across all GPUs.
Nailed the architecture and training.
The scaling laws shifted from Kaplan to Chinchilla, proving that parameter size and data volume must scale equally. Massive models need massive data. We transform the raw model into an assistant using instruction tuning and align it with human values using RLHF with the reward model or DPO, skipping the reward model via math.
Right, the finishing school.
We cure its isolation by giving it external access via RAG searching databases and SEIken grounding the text logic in physical robot sensors. We shrink the compute costs using PEFT methods like LoRa, the transparent plastic sheet quantization lowering numerical precision via smooth quant and pruning deleting dead weights with Wanda.
And the final grades.
And finally, we grade the model's intelligence on MMLU across 57 subjects while actively battling the alignment tax that degrades reasoning in the name of safety.
If you can articulate that synthesis, you have thoroughly mastered the comprehensive overview of large language models. You understand not just what the AI is, but the physical, mathematical, and historical forces that forged it.
You've made it. You absorbed a 100-page academic paper on advanced artificial intelligence without looking at a single equation. As you park the car and turn off the engine, I want to leave you with one final thought to mull over as you walk into the exam room.
A little parting gift.
Exactly. Early on, we discussed the concept of emergent abilities. These models developed skills, reasoning, translation, logic that they were never actually programmed to do simply because they got massive enough. They simulated intelligence just by playing a trillion-round game of guessing the next word.
What?
But Chinchilla's scaling law tells us we just need more data and more parameters to unlock more performance. Right now, in server farms around the world, the industry is training models an order of magnitude larger than anything mentioned in this paper.
Oh, definitely.
If making them bigger unlocks secret, hidden skills, what undocumented, unimaginable abilities are quietly waiting, currently evolving, in the massive neural networks digesting the internet right now? What will they learn to do tomorrow that we didn't teach them today?
It is the single most thrilling and consequential question in human history.
Good luck on the exam. You are prepared. Go ace it. See you on the next deep dive.